Hello and welcome back. We're moving on to section 1B, dimensional analysis, metric conversions, temperature scales, and density. Let's talk about dimensional analysis. What is that? Well, that's solving problems using equality statements. Let's start with an example. How many Japanese yen can you get from $5? First, you make an equality statement between yen and dollars. So we know that $1 is equivalent to 113 yen. And this equality statement can be written as a fraction or as a conversion factor. We know that $1 is equivalent to 113 yen, or 113 yen is equivalent to $1. So if we have $5, we place our equality statement or conversion factor next to it so that the dollar signs, these cancel. And we're left with one unit, the yen. Or, first thing we do is start with our known, our given. Then we find a conversion factor that will help minimize the units to give us the units we want. So we know that, we'll put the dollars on the bottom, we know that $1 is equal to 113 yen. So the dollar sign on the top divides by the dollar sign on the bottom, which cancels, which leaves you with yen. So we're left with 5.00, right? 5.0, $5 times 113 yen, which leaves us with the unit of yen and a number of 565, a value of 565. So we know that $5 is equivalent to 565 yen. Pretty simple. So how many British pounds can we get for $5? Well, we know that 1 pound is equivalent to $1.30. So we can write an equivalence statement or a conversion factor stating it either way. Dollars on top, pounds on the bottom, depending on what we're using. So we're given $5, correct? 5 US dollars, I guess. And then we're using a conversion factor with pounds to dollars, with dollars on the bottom. The dollars will cancel. We're left with pounds. So again, we start with dollars, what we're given, 5.00, right? $5. And a conversion factor is 1.00 pounds is equal to or equivalent to $1.30. So the dollars will cancel. We're left with pounds. So 5.0 times 1 divided by 1.30 will give us 3.85 pounds. Simple. Always write what you're given first. Then select and manipulate a conversion factor to get the units on the bottom, what you started with, and you're left with the remaining units, which are, in this case, pounds. Make sense? So how many Japanese yen can you get for 5.00 British pounds? Well, first, we need to make an equality statement between yen and pounds, but there isn't any. So this will be a multiple step problem. We know that $1 is equal to 1.30, 1 pound is equal to $1.30. And we know that 1 US dollar is equal to 113 yen. So make the conversion one way, and then we'll make it to the second currency. So we know that 5 pounds, correct? We're going to convert this now to dollars. And we know that 113 yen is equivalent to $1. So dollars will cancel, and we're left with yen. So 5 British pounds is equivalent to 735 yen. As of today, yesterday, we don't know. Currency keeps fluctuating. So how many miles are in 1 million inches. Notice. So with this dot, how many significant figures does the answer have to have? Let's see. So we have a decimal, so we have to come from the left. The first non-zero number is here. So 1, 2, 3, 4, 5, 6, 7 significant figures. Remember that? Okay, so we know that 1 foot is equivalent to 12 inches. And we know that 1 mile is equivalent to 5,280 feet. So we start with our 1 million inches. Find a conversion factor that allows us to get rid of the inches. They're gone. Then another conversion factor to convert from what? Feet to miles. Right? We have it to feet. Now we have to get it to miles. We know that 1 mile is equivalent to 5,280 feet, so the feet cancel as we move across. And we're left with an answer of 15.78283 miles. So there should be 7 significant figures. 1, 2, 3, 4, 5, 6, 7 significant figures at the conclusion. So let's try it down here. Always write what you're given, right? You're given 1 million inches. And we know a conversion factor is 1 foot is equivalent to 12 inches. So the inches go away. And you're left with this. Then we know that we want to get these feet to miles. We know that 1 mile is equivalent to 5,280 feet. So now the feet cancel. We're left with miles. So we multiply it across. The answer is this divided by that. So 1 million divided by 12 times 5,280, that'll be on the denominator. So the numerator, is going to be 1 million miles divided by 12 times 5,280 feet will give us 63,360, no units because they're gone. So we take that 1 million miles divided by 63,360 and we come out with 15.78283. Correctamundo. Beautiful. Let's go on. So how many seconds are in 1 year? We know that 1 year has 365 days. 1 day is equivalent to 24 hours. And 1 hour is equivalent to 60 minutes. You see what I'm doing? I am jogging my brain to say, okay, how are these related? Well, I know something about years and days, and I know something about hours in a day, and I know something about minutes in an hour. So I make a list and then select from this list what I need. So I'll start with our given, which is 1.0000 years. Find a conversion factor that fits to eliminate years. Years are gone. Then I know there's 24 hours in 1 day. This makes the day units disappear. Then we're going to convert what's left. We know that 24 hours, that 60 minutes is in 1 hour. Okay, so those cancel. And we're left with seconds. 60 seconds is equivalent to 1 minute. And then those units cancel and give us 31,536,000 seconds. There are 1, 2, 3, 4, 5 significant figures in our initial part of the problem. And there are 1, 2, 3, 4, 5 significant figures in our final answer. Remember, if there's no decimal, you come from the right. First, second, third, fourth, fifth significant figure. Perfect. Let's convert 35 miles per hour into feet per minute. Oh boy. Don't worry about it. Let's attack it one piece at a time. We know that 1 mile is equivalent to 5,280 feet. Okay. We also know that 1 hour is equivalent to 60 minutes. We know that 35 hours, right, in 1 hour, 35 miles in 1 hour, which are given. We'll use the first conversion factor to get rid of the miles. We're left with hours and feet. Use our second conversion factor. 1 hour is equivalent to 60 minutes. So now we get rid of the hours. And we're left with 3,080 feet per minute. Does that make sense? You keep finding conversion factor enables us to eliminate any remaining units, which gives us the final units we need of feet divided by minutes of what's left. Genius. Now we started with 2 sig figs. We have to round this to 2 sig figs. So to go round to 2 sig figs, you come from the right. You have 3 here. Let's put a line after the second one, right? And then this 8 makes a 0 a 1, which gives us 3,100 feet per minute. Okay? The number of significant figures in your answer should match the significant figures of what we started with. We have 2 here, and we have 2 at the end. Let's talk about temperature scales. Temperature is a property of a system based upon the average energy of the particles composing the system. There are 3 common temperature scales: Fahrenheit, Celsius, and Kelvin. Water freezes at 32 degrees Fahrenheit, or 0 degrees Celsius, or 273 kelvins. No degrees, because it's absolute. And water boils at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 degrees Kelvin. We know this Celsius and Fahrenheit scales pretty well, but this Kelvin scale is a little new to us. We use it because it's an absolute scale. You'll see. So here's our typical scale, a thermometer in Celsius and in Fahrenheit. We know that the freezing point of water is 32 degrees Fahrenheit or 0 degrees Celsius. We know the boiling point of water is 212 degrees Fahrenheit or 100 degrees of Celsius. And room temperature is about 68 degrees Fahrenheit or 20 degrees Celsius. So we have specific conversions, factors and equations or formulae that we can convert Celsius to Fahrenheit. This is one we would use. I'll give you these on the exam. Don't worry about it, okay? So what is Celsius temperature when it's 95 degrees Fahrenheit? Well, first, we'll write what we're given, right? Fahrenheit equals 95 degrees Fahrenheit. So we're solving for F. We're substituting for F, correct? Then we'll try to substitute what we have. Let's see, let's take this 32, right? Add a negative 32 to it, which gets rid of it here and puts it over here as a negative 32. You're left with the Fahrenheit degrees subtracted 32 degrees from that should equal 1.8 times the degrees Celsius. So when we rearrange this formula, we divide both sides by 1.8. That eliminates the 1.8 on this side, and we'll divide it by 1.8 on this side. So we're left with Celsius equals the degrees Fahrenheit minus 32 divided by 1.8. So we now can substitute our 95 degrees Fahrenheit minus the 32 divided by 1.8 gives us degrees Celsius. So 95 degrees Fahrenheit is equivalent to 35 degrees Celsius. We're using this formula, moving it around, solving for C. So scientists are in accordance, they're in agreement that there's a lowest possible temperature, and that's negative 273 degrees Celsius. But with an absolute scale, we use 0 as its lowest possible value. And Kelvin is an absolute scale. So we compare Kelvin and Celsius, or centigrade, right? 373 Kelvin is 100 Celsius. 0 degrees Celsius, our freezing point, is negative 273. 273 Kelvin, And absolute 0 is equal to negative 273 degrees C. Kelvin is an absolute scale, so we'll start at 0 and go as high as we have to, as necessary, to solve many of our problems. Absolute 0 is equivalent to negative 273 degrees Celsius. Absolutely. Okay? Makes sense? So there's also a formula that the number of kelvins is equivalent to the degrees Celsius plus 273. That will give us the number of kelvins if we're given a C. If we're given a Fahrenheit temperature, we can convert that to a C, a Celsius temperature. Add 273 and we'll get the units of Kelvin. So we move into metric conversions. So how many kilometers is equivalent to 525 meters? Well, we know that our base unit's going to be meters for distance, liters for volume, and grams for mass. So initially, we're moving from a large unit, a big unit of kilometers, to a very small unit of meters, or our base units. So let's start out with a conversion factor, converting or relating kilometers to meters. Kilometers to meters. The difference here is going to be 3 decimal places, or 1,000. So 10 to the third meters is equal to 1 kilometer, or 1 kilometer is equal to 10 to the third power meters. So we start out what we're given every time, 525 meters. We find a conversion factor that eliminates meters, which is 1 kilometer to 10.3 meters. And what we have left over is kilometers. So our answer is 0.525 kilometers, a little bit more than a half a kilometer is going to be 525 meters. Well, there's an easier way. I developed this Dr. P metric conversion elevator. If we started with kilometers up here, we're going to come down 1, 2, 3 levels to get to this ground level. So we know that this class is downright tough. So if we're moving down from kilometers to meters, or kilometers to meters, we're going to move the decimal place 1, 2, 3 places to the right. So if we started out at 525, right? This case, we're going meters to kilometers to figure it out. We're going to move upwards to the left. We're going from meters to kilometers, correct? Kilometers, right? Which is our known, and we're trying to find something we don't know. So 525 meters to kilometers. So we're going up 1, 2, 3 places. So we're going up, move the decimal place to the left. 1, 2, 3. So our answer is 0.525 kilometers or kilometers. It's a little simpler way of doing it, or just consider the conversion factors here between 0 and 3. You're just moving a decimal place 3 places. So how many centigrams are contained in 8.93 grams? Well, we know that the large unit grams equals 10 squared, or 100 small centigrams. So we start what we're given, 8.93 grams. We find our conversion factor, 10 squared, which is 100, divided by 1 gram. The grams cancel, we're left with centigrams. So 8.93 grams is equivalent to 893 centigrams. How many liters are in 25.0 milliliters? 1 liter, right, is compared to 1,000 mLs. So we start out with 25.0 milliliters. A conversion factor is 1 liter is equivalent to 10 to the third milliliters. The milliliters units will cancel. We're left with liters. And the answer is 0.0250 liters. Let's show you an easier way. Okay, so we're converting milliliters to liters. We're going milliliters and we're coming up to liters. 1, 2, 3 steps to get to our base units, right? Which is going to be liters. So we're coming up 1, 2, 3 steps. So if we come up, we go to the left, because this chart is uplifting. Come up and to the left. So if we move this to the left, 25.0, 3 places to the left, 1, 2, 3. There's our answer. 1, 2, 3. This works very well when you're converting within the metric system. Okay? You have a choice. You can use the base units or you can use the elevator. Something a little simpler, something students can grab onto. Okay? Just memorize this. Write this a dozen times. Okay, so how many kilograms are equivalent to 150 decigrams? Well, going from a small number, a unit, to a large unit. So the equivalent statement is a kilogram is equivalent to what? 10 times 10 times 10 times 10, which is going to be what? 10 times 10 times 10 times 10. 10 times 10 is 100, times 10 is 1,000, times 10,000. So it's 10,000 of these for every one of those. 10,000 decigrams for every 1 kilogram. So we're given 150 decigrams. We know that 1 kilogram is equivalent to 10 to the 4th decigrams, or 10,000 decigrams. So that converts to 0.015 kilograms. Or we can use a Dr. P metric elevator, and we're starting out with decigrams, and we're moving up 1 place, 2 places, 3 places, 4 places. So we're going up 4 places on the scale. So we're going to move it to the left 4 places. So if we had 150 decigrams, we're going to move it to the left 1, 2, 3, 4 places. So 0.0150 kilograms is equal to 150 decigrams, and that's our answer. Our initial problem has 2 significant figures, and our final answer has 2 significant figures. Check, we're good. Let's move on. How many micrometers are equivalent to 0.37 centimeters? Let's see, we are going from centi to micro. Micro is very small. So 0.37 centimeters, we use our equivalence factor or our conversion factor of 10 to the 4 divided by 1, right? So we're going from centi down here. So it's 10 to the 4th, right? The difference is 4. 10 to the 4th, 6 minus 2 is 4. So 10 to the 4th, or 10,000 micrometers, is equal to 1 centimeter. So 0.37 centimeters is equivalent to 3,700 micrometers. Or using the elevator, we're going from centimeters down to micrometers. 1, 2, 3, 4 places, or moving down 4 levels. So we're going to move the decimal point to the right 4 places. So 0.37 to the right 4 places is 1, 2, 3, 4. 3,700 micrometers, or little ones. 3,700 little ones is equivalent to 0.37 centimeters, larger ones. Make sense? Now we're going to convert 22.5 milliliters per second flow rate into liters per minute flow rate. So let's start out with our quantity. 1 milliliter is equivalent to 10 to the negative 3 liters. And also, we'll address our time units. 1 minute is equivalent to 60 seconds. So we start out with what we're given, 22.5 milliliters per second flow rate. Use our conversion factor to convert our volume first. So now we have liters. Now we want to move into converting the seconds to minutes. There are 60 seconds per minute. So now the seconds are going to cancel. You're left with liters on the numerator and minutes on the denominator, which gives us a rate of 1.35 liters per minute. So we converted 22.5 milliliters per second is equivalent to 1.35 liters per minute. Let's move on to the property of density. Okay, density has to do with how much mass is compressed or compacted into the specific volume, or how few pieces of mass are compacted or placed into a certain volume of space. So we know that the density of any object or any solution is equivalent to the mass of the object divided by the volume it occupies. Different materials have different densities. Lead is 11.34 grams per ml. So for every milliliter of lead, 11.35 grams is going to occupy that 1 milliliter. Water, 1 gram of water is going to occupy every 1 milliliter of volume. Cork is less dense than water. Air is less dense than cork, and helium is much less dense than air, cork, water, and lead. Make sense? Okay, so how do we solve for mass in this case? Let's review some algebra. So we know that D, the density, equals the mass divided by the volume. We want to solve for mass. We have to multiply both sides by volume, which gets rid of that, and we're left with VD equals the mass. And there's your mass. Now, let's erase this, and let's say for a second we want to solve for volume. Let's say we know what the density is. I'll list my density is a certain number. My mass is a certain number, right? And my volume is undetermined in this case. Okay? So we start out with D equals the mass divided by the volume. We're going to get it out of the denominator first. Multiply times V. We do the one side, do the other side. So we're left with VD equals M. Now we want to divide the left side by D. And we do the one side. We have to do the other side. Divide that side by D. And what are we left with? The volume equals the mass divided by the density. And that's how we solve for those. So we algebraically manipulated this basic formula to determine 1, 2, or 3 of the variables. We're going to use this many times through this class. Okay, what is the density of a solid in which 2.20 grams occupies 150 mLs? The first thing I'm going to do is note that I have a mass measurement right here. of 2.20 grams, list it, take an inventory, and 1.50 milliliters is going to be our volumetric measurement. And there's our V. Now we're left with our density because we're trying to calculate the density. First thing we do is write down what we know, gather our data, and then assemble it in some form where we can manipulate it. So we know the basic formula for density is equivalent to the mass divided by the volume of what we're dealing with. So we know that our mass is 2.20 grams and our volume is 1.50 milliliters. So that gives us a density of 1.47 grams for every ml. That's the density property of a specific solution. So let's try a few problems. What is the mass of 12 mLs of a solid if it has a density of 3.50 grams per milliliter? Well, we know that this is going to be a volumetric measurement, and this is going to be the density measurement, correct? Good. So we take our basic formula, density equals mass divided by the volume. We're going to manipulate that to solve for M. We know we're looking for M. Now we're going to substitute our volume of 12.0 milliliters times our density of 3.50 grams per ml. Right? Multiply this, the mL's on the top, mL's in the denominator of this one. They cancel. And you're left with 42.0 grams. You started with 3 sig figs, 3 sig figs, and with 3 sig figs. It checks out. Okay, what volume does a 6.2 gram of a liquid occupy if its density is 1.4? So what you're given is a mass measurement, 6.2 grams, and you're given a density measurement of 1.4 grams per liter. Okay. So we have our mass measurement and we have our volumetric measurement. We do not know what our volume is. That's what we're hunting for. So we start out with what we know about it. We know that density is equals the mass divided by the volume. We rearrange it to get the volume by itself. Here we go. Now here's our formula. We substitute 6.2 grams for our mass, right there. And we know that our volume, our density is going to be 1.4 grams per ml. The grams will cancel. It's going to leave 4.4 milliliters. Easy. Simple. Okay, let's get a little bit of algebra practice. Let's review this because we're going to use this in the rest of the class. So 6 minus -5. First thing we do to solve for x is to combine like terms. Well, what we do have here on the left side, right, 6 minus 5x equals 6 plus a -5x. That's an equivalent statement. Those are the same thing. So I'm going to add a positive 5x to the left side. That makes that 0. What I do to one side, I have to do to the side. So I add a positive 5x to the right side, which equals 12x plus 2 plus a -x. Well, a -x plus a positive 12 gives us a positive 11x plus 2 equals 6 minus 0. Now I want to get rid of this 2. I add a -2 to this side. That becomes 0. And a -2 over here. So 6 plus a -2 gives us a positive 4 equals 11x. I want to get the bully by himself, or the x by itself, divide by 11. That goes away, and divide by 11 on this side. So x equals 4 elevenths. Or you can divide the 2 and get a decimal. Let's move to this one. We have to use a distributive property, right, to get x by itself. So we're left with 10x plus 30, this times this, plus this times that, correct? Equals 7 times 2 is 14x, plus 7 times 6, which is 42. Now we'll combine like terms. Let's see, take a -10 to this side, that makes it a 0, and a -10 to this side leaves us with 4x plus 42 equals 30. Let's add a negative 42 on this side. That goes away, it becomes 0. And a negative 42 on this side, it becomes a negative 12 equals 4x. Divide by 4 on both sides gets the bully by himself, the x by itself. So we're left with x equals negative 12 divided by 4, which is going to be a negative 3. So x equals a negative 3. Make sense? Simple algebra 1. Now let's solve for the temperature in this ideal gas equation. So to get T by itself, I'm going to divide both sides by NR. I'm going to divide this side by NR. So I'm left with T equals PV over N times the value of R. Straight, simple, algebra 1 simplification. I hope that helps you. So to review for our exam, we have to understand how to use scientific notation, create it and convert it, interconvert back and forth to standard notation. We learn how to read graduated equipment, such as graduated cylinders. We understand the essence of significant figures. Two different rules. One is for addition and subtraction, and a different rule is for multiplication and division. Then we're going to understand operations with significant figures. Metric prefixes, which are going to be milli, deci, centi, what they mean, kilo, nano. Dimensional analysis, how to create conversion factors to solve problems. Know metric and time equalities. Understand temperature scales. There are 3, right? There are Celsius, Fahrenheit, and kelvins. Degrees, and just straight kelvins. Know the equalities between them. In other words, know the formulas. I'll give those an exam, but remember the formulas. Density, solve for D, M, or V, which we just did. And there you go. And there's 1B. Let's move on to section 2A.